Okay, well, why don't we get started? Welcome everybody to the SIAM conference on mathematics of planet Earth, our plenary session. Today we have Professor Claudia Schillings from the University of Mannheim. And I will just give a little bit of an introduction, and then, well, I suppose first, before I introduce the speaker, the way we're going to conduct this plenary talk is Professor Schillings will speak for 10 or 15 minutes in a sort of introductory way, and then she will take some questions, and then she will complete the talk and take another set of questions. In order for her to take the questions, I'm asking that you wait to put your questions in the chat or to raise your hand with the Zoom software until she asks for the questions, so she doesn't have to search back through the chat box for them. Okay, so Professor Schillings' work focuses on optimization and uncertainty quantification. And an important example of the type of work that she does in this contribution to uncertainty quantification is a rigorous proof of convergence for the case of a finite number of ensembles in the long time limit. And this type of result is really important because previous work that was focusing on the case of an infinite number of ensembles, you could show, for example, that even though the problem would converge, it might converge to the wrong answer. So these types of proofs where we can say something about the real case we're going to be looking at, especially for optimization, are really important right now. I think rigorous mathematical results in the case where we have finite numbers of things with maybe large unknowns, or for finite epsilons versus infinite epsilons, I think are going to figure large into the questions we want to answer about our changing environment in the coming years. So with that, Claudia, you can take over.
Thank you very much. So thank you very much for the introduction, and also thank you very much for the invitation to give you a talk on my work on the identification and minimization of uncertainties for large-scale problems. In particular, I will talk about the analysis of the Ensemble Kalman inversion in this talk here. And before we start, I would like to mention that this is joint work with Dirk Plemke from Augsburg, Niels Schade from KAUST, my PhD student Philip Good from Mannheim, Andrew Stewart, Caltech, Shin Tong from Singapore, Philip Bakker from Erlangen, Nuremberg, and Simon Weismann, also a PhD student in my group here at Mannheim. Okay, so before we start, let me give you a brief outline of the talk. So first of all, I would like to give a short motivation. I will show some applications we are interested in and discuss or introduce the inverse problem we are interested in solving. Then we will discuss the Ensemble Kalman inversion as a method to estimate the unknown parameters in the inverse setting. We will discuss a bit of the theory we developed for the Ensemble Kalman inversion, which is based on the derivation of the continuous time limit of the algorithm, and then the investigation of the long time behavior of quantities of interest in the differential equations. Then the last part of this talk will be on a quite recent work where we used the Ensemble Kalman inversion for neural network-based one-shot inversion. So here we try to solve the inverse problem simultaneously with the forward problem, and designing with the simultaneous optimization and solution of the forward problem, designing a very efficient method. And then as usual, a short summary and outlook to future work. Okay, so let's start with the motivation. Why are we interested in the Ensemble Kalman inversion, and for what kind of applications we use the Ensemble Kalman inversion? So in practice, it is widely used to estimate unknown parameters for measurements in various fields. So the first application I show here is the one you are probably most familiar with, namely numerical weather prediction. Here, the idea is to use the Ensemble Kalman inversion in order to estimate unknown parameters in our models and thus improve the accuracy of our computational models. That means improve the forecast. So what we have in this setting, we have different observation systems giving us a lot of data from which we can estimate the unknown parameters and then improve the accuracy. The second application we are interested in are biological systems. Here we can see an example of a biochemical network. They are usually modeled as high-dimensional ordinary differential equations with a lot of parameters which we don't know, the reaction rate constants in this setting. But usually we have a lot of data with those biological systems, so we can use the data in order to improve our knowledge on the unknown parameters, on the unknown reaction rate constants in this setting. And the last one is a quite recent application we started looking into. So this is the training of a neural network. We can think of the training of a neural network as an inverse problem and use the Ensemble Kalman inversion as a gradient-free method, as an alternative to a stochastic gradient method, for example. And it turns out that the Ensemble Kalman inversion works quite well in this setting and shows comparable results to state-of-the-art gradient-based methods. Okay, I will come back to this point here in the second part of my talk. Let me now, first of all, introduce the inverse problem which we want to solve in this setting. So this is a quite abstract mathematical setting in order to describe the inverse problem. We denote here by U the parameter function or parameter vector. We usually want to work in the infinite dimensional setting. So we should think of U as a parameter function rather than the finite dimensional parameter vector. Then P denotes here in this setting the state vector or state function, and S denotes the solution operator of the underlying forward model. So this one here is typically a highly complex model, like modeled by a partial differential equation or ordinary differential equation or stochastic differential equation, whatever you use in order to describe your physical system. What we should keep in mind during this talk here is that one evaluation of the solution operator is typically very expensive because we have to solve the underlying system. So that means we have to solve the underlying differential equation. Okay, then for the applications we have in mind the forward problem, which is to find the state P for given parameters U. This is typically a well-posed problem in the sense that we have existence and uniqueness of solutions, and we have also stability. Whereas in the inverse setting, where we want to find the unknown data U from noisy observations, and we assume here additive normally distributed noise throughout this talk for simplicity, we can generalize some of the results also to other noise models here. This is typically an ill-posed problem because we want to find possibly infinitely many parameters from usually a finite number of observations, which might be subject to noise as well. So that means we can't expect uniqueness in this setting. Sometimes existence is also an issue, and stability as well. Now, how can we solve such an inverse problem? Well, there are mainly two approaches to solve such an inverse problem. The first one relies on a deterministic optimization problem, where we minimize in the objective the so-called data misfits, so the difference of the data and the outcome of our model. Of course, we want to match the data in some sense. Since this the inverse problem is an ill-posed problem, we need some additional regularization. And in this setting here, this is just a very simple regularization by an additive regularization function in this setting. So the idea of the regularization is to stabilize our optimization procedure and also to pick one specific solution in the solution manifold when minimizing just the data misfit in this setting. So that means when using the deterministic optimization approach to inverse problems, we have to solve a large-scale deterministic optimization problem There are efficient methods to do so. However, we have no quantification of the uncertainty in the unknown U. So we don't know how reliable our estimate will be. And sometimes it's difficult to come up with a good choice of the regularization term, since, of course, the regularization term or the choice of the regularization term strongly influences the solution. Because, as I mentioned, the idea is to pick one specific solution in the solution manifold. So it's crucial to find a good regularization term here. There's a nice connection to the Bayesian approach to inverse problem, which I will introduce now, and we will discuss the connection later on in more details. Let me first introduce the Bayesian approach to inverse problems. So here we interpret all the variables as random variables. We assume, according to our prior knowledge on the unknown parameters, a prior distribution on the unknowns. And the goal of computation is to compute the so-called posterior distribution, which is the conditional distribution on the unknown parameters given the data. And then typically we use the posterior distribution in order to compute moments of system quantities under the posterior. Just to give you a picture of what we are doing. So this is our prior assumption here. It's just a simple Gaussian prior in 2D. We obtain the noisy data. We want to use the information in the data in order to update our information on the unknown, in order to improve our knowledge on the unknown. So we condition on the data, obtain the posterior as a solution of the Bayesian inverse problem, and then use the posterior distribution in order to compute moments of a quantity of interest, for example. Okay, in a mathematically more rigorous way, we can describe the Bayesian setting as follows. So assuming that the so-called forward response operator, which is just the composition of the observation operator and the solution operator, is a continuous one, and we have finite observation, a finite number of observations, full prior measure on the parameter space, and the posterior measure is absolutely continuous with respect to the prior. And we have this expression here for the Radon-Nikodym derivative. Okay, so let me guide you now through this expression for the Radon-Nikodym derivative. We have phi here, which is called the potential or data misfit. We have seen this term already in the optimization approach to inverse problems. So this one here measures the difference between the outcome of the model and the observations. We have this quadratic term here, or the quadratic form of the potential, because we assumed additive normally distributed noise. Okay, so what you should keep in mind is that, of course, for one evaluation of the data misfit here of the potential, we have to solve the forward problem because it involves the solution operator of the underlying physical system. So in other words, evaluating this Radon-Nikodym derivative here is very expensive because for each evaluation, we have to solve the underlying system. Okay, so the exponential of the negative potential or data misfit here, this is called the likelihood. This gives us an idea how likely the data is we observe. And this corresponds to a weighting. So this one here says how much we should trust the data and how much we should still rely on our prior knowledge encoded here in the prior distribution. Furthermore, Z here is just a normalization constant, ensuring that the posterior measure is again a probability measure. Okay, now in the Bayesian setting, we have a quantification of uncertainty in U and system quantities. We have well-posedness of the inverse problem because we have a regularization via the prior distribution. We can incorporate prior knowledge just by choosing a proper prior distribution. However, only in very simple cases, we have a closed form solution for the posterior distribution. And in most of the applications, in the more interesting ones, we have to somehow approximate the posterior. And as I mentioned in the beginning, we are usually working in the infinite dimensional setting where we have infinitely many parameters which we want to identify. So that means we have to somehow approximate an infinite dimensional objects, and this is typically very expensive. Now, before discussing methods to approximate the posterior distribution, let me first discuss the connection between the optimization approach and the Bayesian approach to inverse problems. So let us restrict the discussion to the finite dimensional setting now and a Gaussian prior distribution. Then in the optimization approach, we consider the following optimization problem. We minimize again the data misfit, and now here we consider a very specific regularization function, namely a Tikhonov type regularization. This is just a quadratic penalization of the unknown u. Now in the Bayesian setting, as I said, the solution to the Bayesian problem is the posterior distribution. What we can do in the Bayesian setting is compute a point estimate, namely the most likely point. So that means we want to maximize the posterior density in this setting. And this corresponds to the so-called MAP estimate, the maximum a posteriori estimate. So that means in this setting here, we have to compute the maximizer of this functional here. This is proportional to the posterior density, this functional. So the first term here is the likelihood, and the second term in the exponential stems from the fact that we assume the Gaussian prior distribution. And now you can clearly see the connection because the maximizer of this functional here is of course equivalent to the minimization, to the minimizer of this function here, because it's just the negative log posterior density. Okay, so there's a very nice connection between both, and we will explore this connection also when analyzing the performance of the Ensemble Kalman inversion. Alrighty, all right, okay, so let me just say a few words on the assumptions here. There is also some work in the infinite dimensional setting connecting those two, and also for more general prior classes than the Gaussian prior here. Okay, now coming back now to the solution of the Bayesian inverse problem. What do we do to approximate the solution, the posterior distribution? I would say the gold standard is to use the Markov chain Monte Carlo method. We have a nice convergence analysis of the MCMC method available. We have dimension robust versions, so you can use it in the infinite dimensional setting. We have multi-level strategies in order to reduce the computational effort, improvements by local approximation. However, in general, you have to do millions of forward evaluations in order to produce your samples from the posterior distribution. And in for some applications, it's just not feasible to do that many forward evaluations. Then, of course, you could also use approximations of the forward problem or of the posterior just by exploiting additional structure, you know, regularity, for example, with Gaussian approximations, trying to spot maps. But sometimes you just don't know any structure you can exploit here. And in those cases, the Ensemble Kalman inversion is widely used in practice in order to produce a relatively cheap estimate of the unknown parameters. So let me summarize. Fully Bayesian inversion is often too expensive. The Ensemble Kalman inversion is widely used in practice to get a good estimate of the unknown parameters. However, there's only little analysis available of the accuracy of the Ensemble Kalman inversion, and that was the aim of our work. So we want to build analysis of properties of the Ensemble Kalman inversion for fixed ensemble size. So we were interested in doing the analysis for a fixed ensemble size instead of the large ensemble size limit, because with the fixed ensemble size, that's usually the setting you use the Ensemble Kalman filter or inversion in practice. But how could we do that? We derived the continuous time limit of the algorithm and analyzed properties of the corresponding differential equations. I have to say that our theory is so far, or most of it is so far limited to linear forward response operators, and we will assume from now on that this forward response operator is a linear operator. Of course, you could say, well, that's quite far away from the applications I've mentioned in the beginning. However, it is, of course, a first step towards the nonlinear setting as well. And I should mention that we don't need any Gaussian assumption to do the analysis. Okay. So let me introduce the Ensemble Kalman inversion for our inverse problem. So it is based on the well-known Kalman filter, where we have the following situation. We work in a Gaussian linear setting. So we have a Gaussian prior assumption. We have a linear forward model so that we can use our model to predict the outcome, obtain the measurements in one iteration, do the update steps, so condition on the measurement data, and get an update, compute this posterior distribution in this setting. And because everything is Gaussian and linear, we know the posterior is Gaussian again, and then iterate in a sequential way. So we assume usually in this setting that we have sequential data ahead. Now with the Ensemble Kalman filter, this is a generalization to the nonlinear setting. So we use an ensemble of particles in order to approximate our distributions here in this setting. And then of course, the update step for nonlinear forward models is just an approximation, a linear approximation towards the posterior distribution. Now that is the Ensemble Kalman filter for sequential for filtering for sequential data collection. We want to use the Ensemble Kalman filter in the inverse setting. So what we do here is we introduce an artificial time. That means we use the measurement data, assume that we have access to all the data, and we assume we use the measurement data in each iteration. So we have here repeated use of the measurement data. Of course, we have to account for it. But when using in each iteration the same measurement data, we introduce, so to say, an artificial time dynamical system, so that we can apply the Ensemble Kalman filter in our inverse setting. Now, let me say that again. So keep in mind the Ensemble Kalman filter estimates sequentially the state of a time-dependent dynamical system from noisy observations. We work in the inverse setting here and call this from now on Ensemble Kalman inversion, where we introduce an artificial discrete time dynamical system which maps the prior into the posterior distribution. So even though we have, for example, time-dependent forward model, we assume that all the data is at hand, use the data in a sequential, use the same data in a sequential way, and that corresponds to introducing an artificial time. So that means we work with this bridging sequence, which maps the prior distribution into the posterior distribution. Of course, as I said, we have to account for this repeated redundant use of the data. And we do this by an amplification of the noise covariance at each step in order to end up with a posterior distribution. And then this is just, I think you are all familiar with this one. Then we just use the Ensemble Kalman update formula. So we use our ensemble of particles in order to approximate the empirical mean and empirical covariance, and then use the Kalman update formula, so this linearization step, in order to condition on the data. And again, you see here the scaling of the covariance noise, which accounts for the repeated use of the data. Okay, so then there are, of course, different variants of the Ensemble Kalman filter. I will talk here about the Ensemble Kalman inversion with the perturbed observations, so the original form of the Ensemble Kalman filter, so that we end up with this iteration for each particle. Again, you can see here the amplification of the noise, which stems from the fact that we introduced this artificial time. And I would like to stop here and see if there are any questions on this setting before I go to the analysis. Let me check the chat maybe. There are No questions so far. Check once again. Okay, doesn't seem to be the case. Perfect. So hopefully the setting is clear. Have you spotted any questions? Did I?
No, I was going to say, I think, I think it's good if we go on anyway because of the time.
Okay, perfect.
Yeah.
Okay. So this is the setting we work in to do the analysis. So what we have here is we interpret the Ensemble Kalman inversion iteration as a time discretization of a corresponding limiting SDE in this setting here. This is the continuous time limit of this iteration here, which we derive just by letting the artificial time step, which we introduced, letting this one go to 0. Okay, so then we end up with this limiting stochastic differential equation. We obtain a stochastic differential equation because we consider here the version with the perturbed observations. Okay, so then we use this one in order to analyze the algorithm. So the aim of our work was to analyze convergence to the minimizer of the regularized data misfits. So we considered in the noise-free case the convergence to the minimizer of this data misfit, or in the noisy case to the regularized data misfit function. Okay, so let me say a few words, because in the inverse setting, we know that the Ensemble Kalman inversion doesn't produce samples from the posterior distribution. So we can't expect in this setting, in this basic variant, convergence to the posterior distribution. There are simple counterexamples available. However, we can prove convergence to a point estimate, namely the map estimate in this setting. And that's also the viewpoint which we will adopt here in this talk. So we will investigate properties of the Ensemble Kalman inversion as a derivative-free optimizer of this regularized data misfit function. Okay. So let me just give you an idea of what we did. So first of all, we ignored the stochastic part, and I decided to show you this approach here as well because it reveals a lot of structure. So this is then the limiting ODE when ignoring the stochastic perturbations. And we can see that this is just a preconditioned gradient flow where we have here the gradient of the potential. We have a non-linearity here because we precondition with the empirical covariance, but when analyzing the ensemble collapse, so when analyzing the speed of convergence of this matrix here towards 0, then we could prove also convergence to the minimizer of the data misfit. In a second step, we looked into the analysis of the stochastic differential equation, so the original version, with the perturbations of the observations. The quantities we were interested in are, well, first of all, we wanted to show global existence of solutions of this stochastic differential equation because it corresponds to a well-posedness of the algorithm. And we were interested in quantifying the ensemble collapse because, as you might know, when understanding, so the particles converge at some point all to the mean, and this is very important to understand because it is closely related to the convergence of the particles or the Ensemble Kalman inversion estimate to the true parameter. So this is an essential step to prove also convergence of residuals. So what we did is we considered the following quantities. We considered the spread, the difference of each particle to the empirical mean in the parameter space and observation space, and also the residuals, so the difference of each particle to the true parameter in the noise-free case, or to the Tikhonov minimizer in the noisy case. Now, what we could prove is, first of all, the well-posedness. We used here the famous subspace property of the Ensemble Kalman inversion. So we could show that the estimate lies in the linear span of the initial ensemble. And then basically this allowed us to work in the finite dimensional setting, namely in the subspace of the span of the initial ensemble. And then we could prove by quite standard arguments the existence of a unique strong solution of the stochastic differential equation. And this corresponds to a well-posedness of the Ensemble Kalman inversion. And in a second step, we analyzed the ensemble collapse, and we could prove convergence rates for moments of the spread in the observation space, as well as almost sure convergence with a rate beta over 2, where beta is between 0 and 1. This is all in the observation space, and in the parameter space, we could prove that the second moment of the spread is monotonically decreasing, as well as the residuals. In order to get convergence in the parameter space, we need additional assumptions on the forward model. Okay, and then for the convergence, well, we needed variance inflation in this setting here because, well, I just showed you because of the ensemble collapse, we know that those matrices here in the finite dimensional setting, they converge the empirical covariance, they converge to 0, and they converge too quickly to 0 to get convergence of the estimates. So we considered here a variance inflation, and then with the variance inflation, we could prove convergence of the residuals in the observation space in moments and almost sure convergence. And this result holds true in the parameter space when imposing additional assumptions on the forward problem. Okay, so that was just a very rough sketch of the analysis we did in this setting for finite ensemble size. Of course, there's much more work. I would like to mention also the work on the regularization. In the case of noisy data, what I just showed you was in the noise-free case. And then this is also a very important point, I think, for practice, because in many applications, we have additional constraints on the unknown parameters on the state, which we need to incorporate. And there has been some recent work in order to incorporate the constraints also in the Ensemble Kalman inversion. And also, of course, the nonlinear forward problem is also something we are working on. Okay, so that was on the analysis. Let me now show you a very nice application where we use the Ensemble Kalman inversion in a one-shot, so-called one-shot framework. So let me explain what the one-shot framework is. Well, let me go back to the optimization problem. So with the optimization problem, we want to minimize in the objective the data misfit plus some regularization term. We ignored so far the fact that we have a forward model because we use the so-called black box ansatz, where we use the solution operator of the forward model in order to formulate, in order to get an unconstrained optimization problem. So what we did is we eliminated here the state in the optimization problem by using the solution operator. So that means in each iteration, for each particle, we have to solve the forward problem exactly. And this is, of course, very expensive. And maybe we don't need to solve the forward problem exactly in the beginning because we are still quite far away from the true parameter. And that's exactly the idea of a one-shot formulation for inverse problems. Namely, we want to keep the state P as an optimization variable and solve the forward and optimization problem simultaneously. That means, in other words, the forward problem is not exactly fulfilled in every iteration. Okay, so how does it work in practice? Well, we considered this model here. So we augmented our model in the following way. So the second line here is just the inverse problem, which we've seen. And we added now the model as an explicit equation here in this setting. We assumed some noise in the Bayesian setting for the model as well. So you can incorporate here model uncertainty if you want to do so. But in a minute, I will also show you a method where you can achieve an exact forward model in the limit with a vanishing noise approach. Now, considering this larger model here, the map estimate is the solution of this minimization problem. So we have now additional regularization. Well, the first one on U we had already, but we have an additional regularization on P as well in this setting. Okay, so in order to achieve that in the limit, we satisfy the forward model exactly, we consider here the vanishing noise model. That means we consider a parameterization of the noise covariance by a parameter gamma, which goes to 0. So in the limit, this one here vanishes, and we work in the noise-free case and solve the forward problem exactly. Now, in the one-shot framework, the map estimate with the vanishing noise is then the following one. It is the minimizer of this function here where we have the data misfit in front. Then we have here the model, and we have this parameter lambda, which is defined as 1 over gamma. So this one here goes to infinity. So we put more and more weight on the forward model so that we solve the forward problem in the limit exactly. And then the 2 regularization functions. Okay. How can we solve this now? Well, we use penalty methods, which are well known in the optimization community. So we solve the constraint problem by a sequence of unconstrained problems with monotonically increasing parameter lambda. I haven't said much about the approximation of the forward problem so far. We use the neural network to approximate the solution of the forward problem, but the method I discuss here is much, much more general. So you can use a finite element approach, DG method, or whatever you want to use to approximate your forward problem. Now, our setting, we were just curious how neural networks perform in this setting. So we use the neural network. We have parameters theta then, which correspond to the weights and the bias in our neural network. And we use the neural network to estimate the state in each point in the domain. And then the Ensemble Kalman inversion as an optimizer. So we have now the augmented parameter space. We have as parameters the original parameters in the inverse problem, and now also the parameters of the neural network. We use this ensemble of particles in order to predict the outcome of our model, use the observations to do the update step and iterate and so on, and use the Ensemble Kalman inversion in this setting to compute the map estimates. So since we are working in the noisy setting, we use some Tikhonov type regularization. So it's even a bigger model we consider here, but this is just some straightforward generalization in order to consider here the Tikhonov type regularizations. Now, how does the algorithm look like? So in this setting, we do the following. We start with an initial ensemble, and then we do the following iterations. We compute an approximation of the minimizer of this function here using the Ensemble Kalman inversion for a fixed penalty parameter lambda. Use then the ENKF estimate in the next iteration and increase lambda and iterate so on. And then in the limit, we can actually prove that in case we have a linear forward model, we solve the original constraint optimization problem, which is this one here. So that means we satisfy the forward problem exactly. Okay, since this is still quite expensive because we have to compute a sequence of map estimates, we considered also a second version of the algorithm where we simultaneously increase also the penalty parameter. And just to conclude, I think I have to stop now. I just want to show you a very simple test example, which we often consider in the UQ community. This is just Poisson equation with an unknown right-hand side. This is the true parameter and the corresponding PDE solution. And we can see here the comparison between the Tikhonov solution, so exact solution, and the Ensemble Kalman inversion estimate in the parameter space and in the observation space. And there is almost no difference, as you can see here. And then having a look at the data misfit, we can see that we have a nice reduction in the data misfit. And for the model error, we can see that for increasing lambda, we reach machine precision, so we can solve the forward problem exactly. Okay, so with this, I would like to stop here. So let me just summarize. I discussed some analysis of the continuous time limit of the Ensemble Kalman inversion. And then the second part was devoted to the application of the Ensemble Kalman inversion for neural network-based one-shot inversion. It seems to be a promising direction also for larger applications. And the link to the Bayesian setting allowed us to come up with a quite general setting where we could prove that we can solve in the limit the forward problem exactly. There are many open questions. The nonlinear setting is one of them, and then also the approximation of the posterior distribution as well. Okay, so thank you very much for the attention, and I'm happy to answer questions.
Thank you very much, Claudia.
Thank you.
I guess I have a few questions myself, but maybe it's more polite to let other people go first. If there are any. Okay, I'll ask my question. You mentioned the nonlinear forward problem is going to be a challenge going into the future, but since I'm interested in myself in weather and climate problems, I'm naturally more interested in that. Could you give us some insight on the sorts of mathematical challenges you might face in doing a similar type of proof for the nonlinear case?
So what we exploited here is this gradient type structure. So let me go back to the analysis, sorry. So you can see that actually from here. So what we exploited here basically is the gradient type structure. Of course, we have a preconditioned gradient structure, but this gradient structure here is only it holds true only in the linear case, because in the nonlinear case, this one here is not anymore. It's just an approximation to the gradient in the nonlinear case. And of course, in the limit where we have an ensemble collapse, this is a good approximation. So you can think of this expression here then as a kind of finite difference for the gradient. So in the limit, it is probably a gradient flow we are doing here, but yeah, it's difficult to quantify then, so to say, the difference to a gradient flow in the nonlinear setting.
Okay,
so that's the main challenge.
Yes, that is a challenge. I wonder, well, I can't help now thinking of models where something like that could be no special nonlinear solutions, but that's for later. I think someone else might have a question. Hang on.
There was a question on the second regularization.
Yes, regularization.
Not entirely sure what second regularization. I think it's referring to the second part probably of the talk. So what we had here is, well, first of all, we considered the regularization here on the parameter u because we wanted to work in the noisy case. So we wanted to show convergence to the Tikhonov regularizer. And then for the larger space, probably this one here, So we included a regularization on the parameter u and also regularization on the parameter theta. But of course, you can also omit this regularization on the parameter theta. It depends on what you want to do. So this one here, but you can include the regularization on the parameter theta, or just set this second scalar alpha 2 here to 0, and then you're back in the original system. I hope that answered the question.
There's another question too, but it looks very, I cannot tell how it's different than the question I asked, but maybe you can, or maybe the questioner can refine the question.
So this question was again on the nonlinear setting. So yeah, so the main challenge is, well, we see in practice it works very well in the nonlinear setting. So there is some hope that we can do the analysis in the nonlinear setting. But of course, it's much more complicated. So yeah, and there is, I should also emphasize the fact that there is also quite a recent paper in the nonlinear, analyzing the nonlinear setting. So this is by Neil and Shin. This is a very specific variant of the Ensemble Kalman inversion they are looking at, but it goes in the direction of a nonlinear convergence analysis. Yeah.
Okay. Okay, great. I guess if there are any further questions, now is the time to ask. And I don't see any hands up either. So, okay, with that, thank you for your talk, Claudia.
So thank you very much.
It's such a strange time for all of us. It's great that we've found this way of having a virtual conference, and so the talks can go on. So thank you for everything.
Thank you.
All right. Okay, thanks everyone. Let's